Welcome to the deep dive. We've got this great stack of your sources right here,
hmm
and they're all zeroing in on something really, really foundational. Stuff you might think is just like math class, ratio and proportion.
Yeah. It sounds academic, but it's everywhere.
Exactly.
Yeah.
So our mission today, looking through all this, is to, well, cut through any confusion maybe.
Pull out the key stuff.
Yeah, pull out the insights and just show how surprisingly simple and honestly powerful these ideas are.
Okay.
Okay, so let's unpack this. Diving in, the first thing about a ratio, it's just fundamental, isn't it? It's a comparison.
Right. A relationship between two quantities. But the sources are clear. They have to be the same kind of thing, same units.
Right, like you can compare, say, 15 apples to 20 apples.
Or, 10 feet to 30 feet, length to length.
Yeah.
And there's a neat detail in the sources about the terms, the names. The first one,
The antecedents, what comes before.
exactly. And the second one, the one that follows after.
That's the consequent. Simple enough.
Yeah, just describes the order.
Right, but here's where, looking at this material, it gets really interesting and maybe a bit counterintuitive.
Go on.
The sources really hammer this. A ratio itself is a pure number.
Meaning.
No units attached. It's just the relationship, the scale between them.
Like a factor.
Exactly. And like a fraction, which the sources explicitly say it's basically equivalent to it, should always be in its simplest form, lowest terms.
So not 20 to 32.
No, you'd simplify that down. What does that divide by 4?
Yeah, 5 to 8 or 58ths.
Right, 5 to 8. That equivalence to a fraction, that's a really powerful point from these sources.
Absolutely. That idea is simplified, unitless comparison. It's key. And it leads us quite naturally, actually, based on these readings.
To proportion.
Exactly, to
Yeah.
proportion, which is simply when two ratios are equal. That's it.
So if the ratio of, say, A to B is the same as C to D,
Then A, B, C, and D are in proportion. Simple equality.
and the sources point out this fantastic property. If you write it like A, B, C, D,
Uh-huh.
the ones on the ends, A and D, they're called the extremes.
And the middle ones, B and C.
Those are the means.
Okay, extremes and means.
And here's the kicker from the material. The product of the extremes always equals the product of the means.
Always. So A times D equals B times C.
Yeah.
And that's not just like a fun fact.
No.
The sources show that's how you solve things. If one value is missing,
You use that rule. If you know the other 3, you can find the 4th.
it just falls right out of the fact that the ratios are equal fractions. Cross multiplication, essentially.
It really is. Okay, and digging deeper into how quantities relate in proportion, the sources make a clear split.
Between direct and inverse, right?
Exactly, direct and inverse proportion.
So direct proportion. That's when, as one thing goes up, the other goes up too by the same factor.
like, buy more apples, cost goes up proportionally.
Perfect example from the sources. Double the quantity, you double the cost.
Yeah.
Assuming the price stays the same, of course. The ratio holds steady.
Right, makes sense. And inverse proportion.
That's the flip side. One quantity increases.
The other decreases proportionally.
Yep. The classic example they give is about work. More workers on a project.
Should take less time, right? Assuming they all work at, roughly the same speed.
More hands make light work, faster work. More men, fewer days. In that case, it's the product of the quantities that stays constant.
Ah, interesting
It
distinction.
really is. And what's fascinating, reading through all these different examples in your sources, is how these seemingly simple definitions,
Comparing, stating equality.
seeing how things change together or opposite,
Yeah.
they build into these incredibly versatile tools.
For solving all sorts of real-world stuff.
Totally. Dividing inheritances, scaling maps or recipes, figuring out speeds, lever mechanics. It's kind of amazing how broad it is.
Okay, so pulling it all together, what's the big picture from these sources? We've gone from the basics, right? Ratios as comparisons.
Pure numbers, unitless, like fractions, simplified.
To the idea of proportion, just 2 ratios being equal, which gives us that super useful extremes and means property.
And we've seen how the sources help us understand how things are proportional, directly moving together.
Or inversely, moving in opposition, which is pretty critical for getting the right answer.
Definitely.
So this deep dive, it really shows that ratios and proportions, they aren't just dusty math concepts. They're like fundamental ways we make sense of relationships between numbers, quantities, the world.
It feels like, based on this material, they're the hidden gears, maybe.
Yeah.
Driving a lot of how we calculate and compare things without even thinking.
Yeah, exactly. Which leads to, I think, a really interesting question for you, the listener, to chew on. Given how basic these ideas are, Where are you already using ratios and proportions, maybe without labeling them, in your job, your day-to-day life?
And maybe, what else could you figure out or optimize if you started applying them a bit more consciously?
Something to think about.